the plan for today, when Myra approached me and she said, "Steve, would you speak?" I said, "Sure, I can do something on waterborne coatings. But let's do a deep dive into spray application, right?" So we're gonna talk about some coating chemistry. But more importantly, we're gonna look at the different ways waterborne coatings are applied on holiday. I'm not sure we've done that before. So indulge me if you've already heard some of this, but hopefully you enjoy it. So a little bit about Peter Lockhart. 111 years in business, based in Germany, family-owned company, fifth generation. Peter is actually the family name. And David Peters, I hope he owns it now. We're new to North America now. It's only been 4 years. We opened our facility in Michigan 2015. Right? So some of you may not have heard of us. Some of you may be saying, well, why after 111 years are you now just coming to North America? Time was right. The company did a lot of homework. The core businesses we're focusing on in North America are the top two: glass decorating and automotive, which explains why we're in Michigan, right? So we're supplying to automotive interiors. Everything we do, though, doesn't matter what market, everything we do is spray coatings. That's all we do. We have a company in California that does coatings for sports and leisure, golf balls, golf clubs, things like that. But our core focus are the top two markets. Now, what we're going to talk about today, strictly for Halloween, right? We're not going to get into flat panel or anything like that. We're going to talk about Halloween, which I think is probably the core business most of us are in, yeah? But today's waterborne coatings, and we'll talk about why one size coating doesn't fit all. Today's waterborne coatings meet the application requirements for beverage bottles, wine, spirit, beer, etc. They meet the application requirements for cosmetic, vastly different than beverage. And they meet the requirements for table. Earlier today, we talked about dishwasher cycles being an important part of that, of course, right? Also in tableware, we include candle glass, which in some cases has yet again a very different set of requirements, right? We all have one thing in common, though. What are we trying to do? Why are we decorating? Whether it's spray coating, screen printing, digital, we're all trying to add brand value, right? That's the one thing we all have in common. Okay. Waterborne coatings have been used to do that for years. Not new, but the technology continues to change and improve. A little bit later in the presentation, we're going to talk about trends in technology and in equipment. And what, as coating technology people, we have to do to keep up with it. There's a lot of talk earlier today about special effects that can be achieved, right? That we can do with waterborne coatings we can't necessarily do with high-fired products. We can do pearlescence, we can do chrome effects, we can do texture effects. Talked about acid etching before, right? It's very common today that beverage bottles, or any kind of glass bottle, when it's given a frosted appearance, it's not an acid etch. It's spray coat, right? People try to get away from the acid coat, the acid etching, for all the reasons that we talked about. Right? At the end of the day, that's what we're trying to do. We're trying to increase brand value for our customers. Our customers' customers. Now, bit of a deep dive into the process. Some of you that are already spraying, you may be familiar with this. Some of you that have only seen some lines, This may be new. Hopefully you pick up some tips along the way. First part of the process is it's got to go through a pre-treatment system. The glass has to be pre-treated. There's been a lot of talk earlier today about flame versus pyrosil. I'm a big proponent of flame treatment, always have been. I will tell you that with UV, pyrosil takes it to the whole other level. With waterborne coatings, they're a bit more forgiving for adhesion, right? Some decorators just use air knives, pass their objects to an air knife to remove the surface dust. Forced air. Just forced air spraying the object to remove dust, right? It's being done. I've always been a proponent of flame or pyrosil in combination, right? Okay. So step one. Step two, we have to apply the coating. How are we applying it? We're applying it via guns, mechanical guns, and we're going to take a look at an anatomy of a gun in a little bit. But I'm also seeing more and more electrostatic applications. We'll talk about why. And really, we're starting to see more electrostatic discs be used in glass coating lines, right? You're applying the coating, we're going to look at the applicators. But then, and this is common, in waterborne decorating, the liquid portion has to flash off. That liquid portion, of course, is water, but there's some co-solvents in there. Yeah? It's not just water. Prior to the coatings, prior to the objects going into the oven, that material has to be given a chance to flash off. Okay? That flash off could be 2 minutes or up to 5 minutes. Sometimes it's heat assisted with some IR. Sometimes the flash off is just ambient, right? But the end goal is all the same. You're removing the surface liquid portion of the coating, right? And then they all have to be heat cured. We're going to talk about drying versus heat curing in a minute. They're not the same, right? Something can be dry, that doesn't mean it's cured. But they all require heat to reach cure. These are all complex chemical reactions that require heat. Now, we'll talk later, that heat can be hot air, it could be IR, could be a combination of both. Right? The objective is all the same. Okay. Then the objects have to go to ambient air to cool down. Right? That doesn't matter how you're decorating the glass, it doesn't matter whose coating you're using, it doesn't matter what applicator you're using, that's the process. Right? One of the things, when I joined Peter Locker 4 years ago, and I said that our roots are in Europe, one of the things we learned very quickly when we started promoting glass coatings in North America is that the glass decorating lines are very different here. And one of the things that blows my mind after all these years, I've not seen two lines the same. Sometimes different within the same decorator, but from decorator to decorator, the lines are different. How are they different? One of the big ways they're different is that we have continuous inline systems where the objects are fed, put through this process, and nobody touches them until the end when they're offloaded. The other thing, and the more common thing that we see in North America, two-stage process, where the glass decorating line is separated from the heat curing and the cooling line. right? So it comes out of the booth, it goes through flash off, it has to be tack-free, and then those objects are sometimes manually moved to the full curing line. So the coating has to be tack-free. Other lines, continuous, nobody touches them. So it doesn't matter if the coating becomes tack-free. Why was that important to Peter Lacca when we started selling in the US? We had to develop technology that was tack-free quick enough so those objects could be moved. Prior to that, the technology we had was all in line, nobody touched it, right? We'll talk a little bit about the benefits of inline systems versus separated systems for a moment, right? Why would a decorator want an inline system? If you're running 10, 20,000 pieces a day of the same size object or similar objects, similar size objects, you're not changing the tooling to fit the glass, right? So it makes sense to have a long run, you're reducing labor costs. But if you're a decorator that has shorter runs, 1,000, 2,000, 3,000 pieces, and you've got to change the tooling 2 or 3 times a day, it makes sense to have smaller systems with less tools so you can change it over quickly to different size objects, right? So that's one of the big benefits. The other benefit is, of course, going to be footprint. So what does an inline? Another thing that all glass coating lines have in common is that they're chain-on-edge systems, right? The objects are loaded onto a chain-on-edge, and they move through the process. Tooling holds them in place. They go to a spray booth, right? Common. But you see the size of that inline system there. You see the footprint on that. That probably has 2,000 plus tools on it. Yeah? A lot of money for the tooling and a lot of time to change them over, right? And a lot of footprint. But if your core business, as I said, is doing 10, 20,000 piece runs a day, not unusual, then a system like that makes sense, right? This particular spray booth has six guns, and we'll show you why the number of guns and the type of guns are important. But once it's filled, it goes through pre-treatment, goes into the spray booth, and the guns are set up accordingly. All right, so what we have here, HVLP guns, high volume, low pressure guns, applying clear coat. There's 3 guns firing here, applying clear coat over 750 ml bottle. Probably saying to yourself, why am I having to apply clear coat over a bottle if it's already decorated? In this particular case, there's a fade pattern applied on the bottom. That means you're putting a very low film weight at this point of the bottom, right? The lower the film weight of the coating, it's true whether you're talking about screen printing or anything. Lower the film weight of the coating, you reduce resistance properties. So to protect it, we always recommend a clear coat over the top. That's what's happening in this process. The other thing that's key to how this is applied is the rotational speed of the bottles. We'll talk more about the variables that affect this, but rotational speed and line speed is very important, right? To get a consistently applied film. Now, I promised you could look at the anatomy of a gun. This is an air atomizing gun, okay? Doesn't really matter who makes them, they all have several things in common. Several keys. The air cap and the fluid regulator, fluid nozzle, and the needle size. Those are the things that are really key to controlling your film melt, right? We'll talk about air pressure and fluid pressure in a little bit, right? The air is focused by something that's called fan control. Yeah? Air pressure is applied to the gun, it applies fluid, fluid pressure pushes the fluid to the tip, the air pressure then atomizes the coating. And the direction of that air is called fanning. Okay? We'll talk about why that's important. That's an H3LP gun, right? There are conventional guns also used, but for glass, we typically see H3LP. High volume, low pressure. They're more effective than conventional guns when applying to a curved object, and they're more efficient. With an H3LP type gun, you're talking about a 40% efficiency transfer rate. Okay? 40%. Then you take the next step up and you go to an electrostatic turbo valve. Okay? It's got about 70% transfer efficiency. What I mean by transfer efficiency, how much of it actually hits the object. How much of the coating lands on the object as opposed to going into your filters. And then you look at an electrostatic disc. Okay? That's got about 80% transfer efficiency. Now, there's differences in cost. Okay? When you're talking about an electrostatic disc, by the way, that disc, when it applies coating, rotates at about 24,000 RPMs. It's humming. All right? 24,000 RPMs. You need a separate room for an electrostatic disc operation. You can have more than one booth in line. I showed you the big inline system. Even if it's a manually transferred system, you can have more than one booth. But if you're doing an electrostatic disc, you must have one booth dedicated just to that disc. Because of the fact that the bottles go around in an omega shape and the disc rotates, right? Electrostatic bells are more common than the disc, and you're typically using those in combination with H3LP guns. The electrostatic disc also rotates very quickly and comes through what's an air cap and a cup at the end of that turbo valve. All right? The combination of H3LP gun used with turbo valve is very common when you're doing 750 mil bottles, because you're hitting the neck with the gun, with the H3LP, and you're hitting the body with the turbo. Yeah? If that makes sense. These type of applicators all require coating manufacturers to design the coating for the proper applicator. Let me tell you what. Picture a disc moving at 24,000 RPMs. You're talking about a waterborne coating. If that system isn't designed to have the stay open time, by the time the droplets hit the object, it's going to be dry, right? Sure, physics, right? So we have to formulate our coatings to be able to do that. Same with an electrostatic belt. But what else is important? When you're talking about an electrostatic charge, we're negatively, during the process, the coating is negatively charged. Right? The equipment is grounded, so it has zero charge. So the coating has to be able to accept a negative charge that's applied to it. So it's attracted to the glass object, which, because it's grounded, has zero charge. Right? That's the concept. So the coatings have to be designed to do that. See? And everybody who hasn't spray coated just thought you were taking a gun and spray painting, right? No, not quite. Not quite. So does that kind of make sense? I know we talked about a lot covered a lot on that slide. All right, we talked about the applicator, applicators. Now we have to deliver the fluid, right, to the applicator. We're typically doing this with pressure tanks, or we're doing it with pumps, okay? Relatively low pressure, we're talking about half of 0.5 bar to 1.5 bar, right? You're delivering it, doesn't matter how you do it, the objective is just to get the fluid to the applicator, right? Okay. The other thing that's key for waterborne coatings is your air line has to be clean, yeah? The old adage, oil and water don't mix. Let's be sure your air lines are free of oil. Those of you that are smiling, you've been through the other side of that where you've got oil in your air lines. Now, atomizing. The whole concept of atomizing a fluid and why atomizing is so important. We have to turn the coating into small enough droplets when it's sprayed, but it's not too fine where it dries when it hits the glass, not too wet where you get blah. That's another technical term. Where you get blobs on the object, right? So air atomizing is incredibly important. If we're putting too much air, it's dry. Not enough air, you're not going to get a good level coating. Ideally, you want the right amount of fluid delivered with the right amount of atomizing pressure to deliver a proper coating thickness. Normally, atomizing pressure is about 3 to 5 bar. Okay? That's typically what we recommend. And that's common, yeah? All right, now, if you get the atomization process right, and your fanning pattern right, if you were to put a piece of cardboard in front of that gun, all right, you're going to get something that looks like that. That's a proper fanning pattern with proper atomizing. Also, it's got the right tip size. For waterborne coatings, we're typically recommending 0.8 to 1.2. 0.8 to 1.0 are the most common millimeter size. So when you get it all right, you get a pattern that looks like that. Get it wrong, and your application looks like that, right? Way too much fanning, your air atomizing is too low, and you're not applying enough fluid. Yeah? Get it wrong again, and your air, you've got too much air. You see you've got dry tips, top and bottom, and your fanning air is not focused properly. So you're just applying in the middle. Yeah? Little nuances of setup make a big difference. Okay? if you talk about everything that affects application, right? Let's start by saying what we're really looking for in glass coatings, 10 to 15 microns dry. Okay? Depending on the solids of your coating, you're typically going to be at about 30 microns wet, 30 to 35 microns wet, right? Depending on the solids. But you're looking at 10 to 15 microns dry, that's what you want. One of the things we have to control through the process to ensure we get there, right? We talked about atomization. How about the viscosity of your coating, right? Too thin, you're going to get runs. Too thick, and you're not going to get an even application. You get the right viscosity, typically measured in gravimetric terms with Ford cups on cups. These are all water-reducible products, so you're adjusting your coatings with water to get there, right? The pressure from that pressure pot has an effect of how much coating you're pushing through the line, right? So you put too much on, that's not going to help. We talked about the fanning, right? The shaping. How about your spray booth conditions? If you're in hot and humid conditions inside your spray booth, depending on where you are, versus dry conditions, that's going to have an effect, right? Sometimes we have to slow the coating down a little bit if you're in a real hot and dry climate, right? Of course, the type of atomizer, we talked about that and the efficiencies from each one. The design and shape of the caps and the cups have an effect on that film thickness. Substrate temperature. We talked earlier about flame treatment, right? So if your glass is hot, when it goes through the spray coating process, the chances are pretty darn good you're going to apply a dry film of coating. Why? The coating is going to dry as soon as it hits the glass. It's not going to get a chance to level and flow. Okay? So flame treatment is widely recommended, but there's got to be enough dwell time by the time the object hits the spray booth so it's cooler. Right? If we give you a waterborne coating that dries too fast, it doesn't matter how slow you're applying it or how much fluid pressure, it's going to dry when it comes, right? So that has a huge impact on how well the coating gets applied. And what about line speed? In that video I showed you, that bottle's probably moving at about 35 pieces a minute. Okay? I've seen some lines that are north of 60 pieces a minute. Not for an object that big. Okay? Not for an object that big. But when you've got an object moving that fast in front of your applicator, that has an effect on how the coating gets applied and how fast it has to level, right? Does it all make sense? It's all tied. If you're talking about electrostatic, the amount of charge that's delivered to the coating has an effect on the amount of coating that hits the object. Typical charge for an electrostatic system is 60 kilovolts up to 100 kilovolts. Right? You don't put enough charge onto it, your particles aren't going to be attracted to the object. Too much, it doesn't do any good. All right? So all of those things have to be controlled when we're accurately applying a film coating. That's what we're trying to get. Okay? Let's talk about let's talk about curing, because this is an important link to what I'm seeing on trends in the industry. Okay? I mentioned earlier they all require heat to cure. I'm pretty sure we all understand there's a difference between drying and curing, right? These have to be cross-linked. It takes heat to cross-link them. Something can be dry, but it's not going to have the physical properties that we're looking for. It has to be cured to get the physical properties, right? How do we accomplish that? First thing we have to do, we have to pay attention to the object temperature. Do we necessarily care about the temperature inside the oven? Well, we do, but it's not the most important point. The most important point is what temperature does the object reach, right? Case in point, 750 ml bottle, thick glass, maybe a very thick base. That object is going to take a lot longer to reach temperature than the thin candle glass, yeah? Make sense? So that's important. Current coating technology, 3 to 10 minutes, object temperature, right? Depending on the coating you're using, depending on the thickness of the glass, and depending on the type of heat we're applying, okay? For years, it's all been done with hot air ovens, right? Very long footprints. Picture an object that has to be in a hot air tunnel for 15 minutes, because it's 5 minutes to heat your object, 10 minutes at that temperature. Picture how long that oven has to be, right? You saw the picture. You get it, a lot of footprint, a lot of expense. So the trend, and we're hearing this across the world, not just here. The trend is moving towards IR coatings, IR curing, or a combination of both, right? To reduce the footprint, to reduce the cost, and to increase your production speeds. Why does IR increase your production speed? The whole reason why IR is more efficient is because you're focusing the energy on the surface of the coating, right? As opposed to hot air, where you're heating up the object, right? A lot of energy is focused to heating the object. With IR, you're focusing on the coating itself. So it's far more efficient, right? But is it all wine and roses? How come every line out there isn't using IR cure? You have to worry about thermal shock. Because if you heat the glass up too quick, Steve mentioned this earlier. Steve, you're getting a lot of billing today, man. Everybody that's speaking went right back to you today. That's a compliment. You talk about thermal shock, right? You heat the glass too hot, IR is very effective, it heats the glass up quickly. If you're working on thin glass, you heat it up too quick, it will burn. So you really have to balance the amount of IR you're giving it, right? That kind of makes sense? And technology doesn't stand still. If we supply you with something that cross-links too slowly, even with IR, you're not going to get the right resistance properly. So as coating manufacturers, we have to balance all of this, right? We have to work with equipment companies to be sure that what we're bringing to market does what it's supposed to do before we bring it to market. Yeah? There's been a lot of talk today about performance requirements, whether we're talking about dishwasher resistance, whether we're talking about the ability to have good enough hardness to go through a high-speed filling line, so it's got to be scuff resistant, whether we're talking about chemical resistance for cosmetic applications. Okay? Our coatings are designed to meet all of those requirements, and they continue to get better. We continue to make the surface harder without making it too hard. We continue to be able to cure faster while still being to apply it through the other applications. Dishwasher resistance. 5 years ago, we wouldn't have made the statement. Today's dishwasher resistance on waterborne coatings far exceeds what it was 40 years ago. It's not a stretch where you get 500 dishwasher cycles, residential dishwasher cycles on today's waterborne coatings. Okay? This technology marches on. And we continue to look to cure lower, right? 160 to 180 degrees C. Okay? That's different from what it was. Okay? Yeah, they're all low VOCs. Less than 10% is common. Yeah? Some have more. But there are definitely low VOC coatings out there. And we all know the drill, right? Everything we do has to be BPA free, has to be Prop 65 compliant. Add to the list, REACH, European REACH compliant, right? When we're talking with some international brands, that's one of the things they say to us. We want to use your coatings here, but they also have to be REACH compliant, okay? So yeah, they have to be REACH compliant. FDA regs for indirect fruit contact, right? That was talked about a little bit earlier, and I think there's the next paper is on that. We don't take that for granted when we formulate these. The other thing is they have to be, they can be single component systems. What do I mean by that? No activators? Yeah? Or they can be two component systems where you're putting an activator in. Yeah? And you're introducing a pot life if you do that. Depending on what you're looking to do, there's both. And a lot of the coating systems today, they're clear coats and pigment systems. So decorators can blend on demand, increasing your efficiencies, reducing waste, reducing leftover material on your shelf because you pre-bought a pre-blended color. Okay? And something that we absolutely always have to pay attention to is when we put a coating out into the market, how do you subsequently decorate? I don't think I see much waterborne decoration at all that isn't labeled, right? Somehow screen printed, digital printed, right? Whatever, it gets a subsequent decoration. The coatings have to be designed to do that. Right? So, I think that's about me done rambling. So I'd like to take the opportunity to open the floor up to any questions. Go ahead, Sean.
I got a quick question. You know, you were doing the clear coat on the fade, and I'm just curious why you went all the way up to the neck. Why not just go up to the fades and save on the chemical process?
It would look different.
It would, okay.
You'd see a difference. You may see some dry spray where we stop the clear coat. So you'd look at the body of it and you'd see, okay, it would be visible.
Okay.
Yes.
Is there such a thing as a UV LED spray coating? Instead
So-
of just spray the bottle and then hit it with UV LED?
Well, so I know that there's work being done on that. I've never seen it used for glass.
I'm just asking, if we can screen print a bottle with UV LED,
Right.
why not spray it? Whack it.
Well, yeah, you know, with UV, there's a few things you have to think of. With UV spray coating on glass, right? It's gonna be expensive versus woodworm coatings, okay? The coating itself I'm talking about. Two, if you're doing a full coat out, is it gonna meet all the compliance regulations? Right? So there are some things you have to consider. I know that there's companies that are doing work along those lines. Yeah, yeah, but for glass decorating, because of everything we have to do and the regs we have to meet, I've always been a fan of them. Right? Okay. Yes, sir.
For aerobel and disc electrostatic,
Mhm.
the charged coating has to be attracted to the glass, but the glass is not a conductor, so is it attracted to the
The
machine?
glass and the equipment is ground.
Right.
So it's neutral. So because we're applying the charge to the coating,
It'll naturally.
it gravitates to the object.
Is that more prevalent a technique in Europe than it is in the United States?
Yes,
Lots of,
Yes.
I haven't seen it in the United States very much.
yeah, yeah. I'm seeing more and more of it,
Yeah.
okay? But it is more prevalent.
If you do the IR cure, you don't need to put any kind of post oven. It comes off a line. The IR is part of the line
Right.
built into the solution.
Right.
And you said shorter conveyors, faster cure times. How short, how fast? I mean, is there a ratio on when you're doing speed?
Well, there is. What we typically see, I mean, if you're doing a 750 ml bottle, we're probably going to run about 4 minutes in the IR. Okay. If we're doing 4 to 5 minutes, if you want to be safe. Okay. If we're doing candle glass, it's going to be maybe that. Okay.
Can you talk a little bit about indirect FDA contact when you're talking about we have a customer who wants the pint glass painted all the way up.
Okay.
What do we tell them?
To the lip and rim, inside the lip and rim?
Not inside.
No, I mean, well, within the 2.5
Yep.
centimeters. Peter Locke has a coating that's compliant.